Hello guys, welcome to another video on physics revision. Today we'll have two questions on the heat radiation part. So let's discuss the first question. I have taken this question again from Olympiad book, and I thought that this question is relevant to our JEE advanced preparation as well. Perfectly black and hot surface is kept at a constant temperature Th. There is another perfectly black cold surface which is parallel to the first one and is kept in constant temperature TL. There is a vacuum in between the plates. In order to reduce the heat flux, a screen is used which is made of N parallel thermally insulated perfectly black plates. In the figure, N is equal to 2. Such a screen is placed between hot and cold plates parallel to them. By which factor X will the heat flux be reduced once a steady state is reached? The edge effects caused by the finite size of the plates can be neglected. So basically this question is talking about reducing the heat flux. Heat flux means the current, heat current, dq by dt. This heat current, as if we do not place any screening here, then the heat current will flow from higher to lower temperature, and definitely for radiation the lower to higher temperature will also there will be a heat. So the net heat current you can calculate. But if I place some screening like this, then what will be the reduction of that heat current, that you need to calculate. So I will suggest you to solve this question for n equal to 2 plates first, and then you can generalize the situation. You try it by your own for few minutes and then again come back to see the solution. Okay guys, so I think you have given it a fair try. Now we will go to the solution page. Look, I have redrawn the situation here. This is the hot plate and this is the cold plate. The plates are maintained by some external power source maybe with temperature Th and TL respectively. So let me first tell you that what happens, what will be the heat current if there is no such screening placed, right? So if no such screening is placed, so suppose this is one plate and I have placed another plate here. So if no such screening is placed, then this temperature is Th and this temperature is TL. So what will be the heat current here flowing from this plate? The heat current dq by dt will be sigma into area surface area of this plate into Th power 4, and similarly from this plate the heat current that is coming here is sigma into A into TL power 4. So if I ask you the net heat current that is flowing from hot to cold surface is sigma into A into Th power 4 minus TL power 4. That is the initial heat current. Let us assume it to be I naught if there is no screening. Now what happens if I place some screening like this? So several things are happening here. Let us try to understand. First of all, that in steady state the heat current will remain the same, right? Heat current is same everywhere in steady state, that we all know, and the temperature of the plates are also constant with time, they are not changing. So this plate always maintained at Th and this is TL. Now the intermediate two plates, let us assume their temperatures to be T1 and T2. So what happens? This hot plate will give a radiation sigma ATH power 4 to this T1 plate, and T1 plate will also radiate heat in both the directions, right? In both the right side as well as to the left side. Right side it will radiate sigma A T1 power 4 and the left side sigma A T1 power 4. and this radiation will come fall to the hot surface, and it will completely absorb it because it is a black body, and this radiation is falling on the first surface, and it is completely absorbing because it is also a black body. Similarly, whenever some radiation here falls to any surface, it is completely absorbed because the surfaces are perfectly black mentioned in your question. So similarly here you can see that the plate at temperature T2 also radiates heat sigma a T2 power 4 to the right, that is absorbed by T1, and this also is radiating sigma a T2 power 4 to the left, which is falling on TL, and it is completely absorbed by the rightmost surface, cold surface. The cold surface is also giving a heat radiation sigma a TL power 4, and that is falling onto the second plate, and it is completely absorbed. So it is the situation. Now if I ask you that what is the heat current flowing in between these first two plates, that is definitely this minus this, right? Sigma a th power 4 minus t1 power 4. Similarly, for between the second and third surface, it is sigma a t1 power 4 minus t2 power 4, and for third and fourth it is t2 power 4 minus tl power 4. You can see there is a series. So if I add all these heat current, sigma I by A I have calculated. So if I add all these I by A, then 3I by A is equal to T1, T1 gets cancelled, T2, T2 gets cancelled. It is TH power 4 minus TL power 4, which is nothing but I naught by A, right? So what is the new heat flux, heat current flux? That is reduced by 1/3. Right? So see, if I use two plates, then the denominator is 3. If I use n such plates, the denominator will be n plus 1. Right? You can also see that T1 T1 gets cancelled, T2 T2, T3 T3 will get cancelled out, like this. It will continue. So the factor this heat flux is reduced is n plus 1. So your answer should be option A, n plus 1. So I hope you have understood this solution of the question. Let's move to the next question. A very similar type of question I will give you, and based on the same concept that you have just studied, but a slight modification I have made in this question. It's my original question. I have not taken it from anywhere. This question says that perfectly black hot surface is kept at a constant temperature TH. There is another perfectly black cold surface which is parallel to the first one and kept at temperature TL, just like the last question. There is vacuum in the space between the two plates. Now in between the plates, another plate parallel is kept. And emissivity of this plate is E. It is not a black body unlike the last one. Find the ratio of the heat flux after and before placing the middle plate once the steady state is reached. The edge effect caused by the finite size can be neglected. You try it by yourself. I am sure you can solve this question and again come back to see the solution. Alright, so we can now jump to the solution page. It says that initially, when there was no plate inserted in between these hot and cold surfaces, as we know that the heat flux or heat current per unit area, that was simply sigma TH power 4 minus TL power 4. That was before. What happens if I place a intermediate plate having a emissivity E? Now look, this hot surface that will give a heat radiation which is falling directly on this plate, but this is not a black body, so it will not completely absorb this heat radiation. Partly is absorbed and rest of the part is reflected back. This dotted line that I have shown in the diagram is a reflected radiation, right? So how much will be reflected back? E times will be absorbed, E times of this power will be absorbed, and 1 minus E times will be reflected. Similar is the situation going on here. This TL will also give up radiation sigma TL power 4 that will fall on the middle plate, and 1 by 1 minus E, and E parts of this will get absorbed and 1 minus E parts will get reflected back, right? And as it has own temperature T that I have assumed, it will also radiate heat at a rate of E sigma A T power 4 in both the directions. Now if I try to write what is the current per unit area in this place, and that will be sigma A Th power 4 minus of 1 minus E sigma A Th power 4 minus of E sigma A T power 4. Right? I have divided it by A, so I have got the flux. And for the second and third plate, the heat flux will be sigma E T power 4 plus 1 minus E sigma TL power 4 minus sigma A TL power 4. So if I just modify this, you can see that this TH power 4 will get cancelled from this side and TL power 4 will get cancelled from this side. So E into sigma TH power 4 minus T power 4 equal to E into sigma T power 4 minus TL power 4. So from here you can also find the temperature of the middle plate. If you just rearrange this equation, you can find the temperature of the middle plate. And once I know the value of T to the power 4, I can put this in any of this equation and I'll find the value of J after placing the plate, right? So this is sigma into E into TH power 4 minus T power 4. So if I put the value of T power 4 in terms of TH and TL, then it is TH power 4 minus TL power 4 by 2, right? Multiplied with the sigma E terms, right? And before it was sigma into TH power 4 minus TL power 4 only. So after by before, if I find a ratio of this, definitely it is going to be E by 2. So that should be your answer, option B. That's all for today. See you in the next video.